As we've studied Newton's laws, we have referred to quantities called vectors, and now we're ready to hit that head on and understand what a vector is, how they're used, and the various nuances. So let's get after it. It's simply a physical quantity which has magnitude and direction. So it has both of those components. And examples of these, some of which we've already encountered: force. You can't have a force without it having a direction. Displacement, velocity, acceleration, momentum, electric fields. There are others. Let's stop there. You can jot those down. Now, how they are symbolized typically is with bold type and an arrow, such as F arrow, A arrow, V arrow. Really, I don't care so much, just kind of showing you how the standard designation goes, how they're represented. Now, a scalar, as distinguished from a vector, is a physical quantity. Aren't you glad it's a physical quantity? With a magnitude but no direction. Magnitude only. Examples of these would be mass, density, speed, time. So for instance, mass, you might say, here is an object of 5 kilograms, north. And something sounded funny about what I said, and it was the north in the description of the object, because it might have a certain amount of mass, certain amount of material quantity, but that has no direction. It doesn't even make sense. It doesn't sound right, does it? 15 kilograms per cubic meter, southwest. All right, you get the idea. So that's the difference. How are vectors represented on paper? You just draw an arrow, but the length of that arrow is determined by a scale, and the direction by a reference frame. There's a reference frame associated with the direction. So a typical reference frame would be north, south, east, west. Kind of like this. North up, south down, east to the right, west to the left. That's typical. Doesn't have to be. You can specify it any way you want. Once you specify the reference frame, then simply be true to that reference frame. Do not deviate from it. Be consistent with it. We are now going to practice drawing some vectors, and my assumption is that you have a geometry instrument that you are going to follow along with in your notes and actually construct these to scale like I'm doing. But if you don't and just kind of watch this, it's fine with me as long as it all makes sense. So here we go. We're going to draw an arrow to represent a force of 50 pounds pointing 30 degrees north of west. Now, 30 degrees north of west. That is the same as 60 degrees west of north. So that means you start west. West would be this way, and 30 degrees north would be swinging 30 degrees north, so it would kind of look like this. That's also 60 degrees west of north. If you start this way, going north, and you swing 60 degrees west, you end up with a vector in the same direction. Now we need a scale so that it fits on our page nicely, and I'm going to choose a centimeter is 10 pounds. So we're going to establish a reference line for these examples. So here we go. We're going to bring our 6-in-1 geometry instrument in. And no, this is not a photograph of the geometry instrument that you got at the bookstore. This actually is the instrument I drew in PowerPoint to make it look that way. So I'm pretty proud of it. Even though PowerPoint isn't a drawing program, I spent more time than I should have spent constructing this thing. But here it is. And now you know how to use a protractor, hopefully. When you make a dot here, then you can determine the angle from that point. We're going to draw a reference line along here, though, at first. That's what we're going to do. So there it is. And put a point right there to start with. And now we're going to determine the angle. So I put that protractor right there. And we're going to go 30 degrees north of west. So right there. Put another dot. Take the instrument away. Bring it back in. and draw it the correct length. 1 centimeter is 10 pounds, so how many centimeters is that? You guessed it, 5 centimeters for 50 pounds. So I'm going to go 1, 2, 3, 4, 5. Now don't be concerned if your geometry instrument, your 6-in-1, does not show the same relative spacing on your page for this, because my scale in my presentation here is not going to match the printed version in your notes. Okay, so anyway, so there it is. It's a proper direction, proper size. Now I'm going to fully label it. 30 degrees is this angle, and it's not really done until you say, ooh, the force is 50 pounds. Now it's fully specified vector. Example 2, velocity 30 miles per hour, 40 degrees south of west. And I have a scale. I'm going to start right here. Bring this in. 30 miles an hour, 40 degrees south of west. Well, here's west. We're going to go 40 degrees south. Well, there's 30, 45, 60. So somewhere in here. There it is. And then let's draw it to the correct size. 1 centimeter is 5 miles an hour. So 30 miles an hour would be, you guessed it, 6 centimeters. So you start your line on a convenient marker on the instrument and then go 6 centimeters. So let's do that. There it is, if I did that correctly. 6 centimeters. Velocity 30 miles an hour, direction 40 degrees, south of west. Example 3. So if you're going along with this and actually constructing them, the good thing is you can pause the video and do it. So we're going to stick a third one in here. 7 miles southeast. This is a displacement vector. 1 centimeter is 1 mile. So southeast. Southeast means halfway between south and east. So there's south, and that's the direction east from this point. So halfway in between, right there. Okay. Draw to the right length. I think that's going to be all the way to here. All right, our construction is going along just fine. We're labeling everything. Displacement 7 miles. Now it's time to add vectors. We just drew a few examples. Let's add, which is just another way to say the vector sum. And it's going to be a single vector that represents both of the other ones. It's going to be equal to the component vectors is another way to say it. So I'm going to add the following vectors, giving the result as a length and direction. Here's vector A and vector B. The idea is that the resultant R is A plus B. Notice I don't have the arrows on these. And as long as you know what you're dealing with, I don't really care if you designate them with an arrow or not, as long as you know how to treat them as a vector. So what we're going to do first then is we're going to add B to A. So we brought our instrument in here so we can measure the length of vector B. Then we're going to parallel move it over to the tip of A. Now you'll notice I'm measuring the length, that's all I'm doing. But in the next little move, what I need to do is bring my instrument in. I flipped it around so that I've got a nice starting marker on the tip of A, and I already know the length of B because I just measured it. And you see these parallel lines? It's a parallel mover. So I've positioned this instrument such that a near line is parallel to the vector. So that's a visual indication. It's an approximation, but it's a good one for our purposes in constructing these vectors. It's good enough to visualize that. So I think you'll all agree that my instrument and this line are parallel. And now, since I have this at the right place, I already took the measurements, so I know how far along here I have to draw my line because of my measurement. So I do that, and I have just moved vector B. It's the same length, same direction right now. And then you start at the beginning of A and draw a line to the tip of B, and that's your resultant. That vector represents the sum of both of those others. So what we have to do is measure the length, and we also have to get the direction. So here's a reference line for the directions, horizontal across the page. And I'm going to take the angle, measure the angle by putting the instrument here, and also measure the length. And when I do that, I get 6.0 centimeters, 8 degrees approximately north of east. Here's east. We swing 8 degrees north using the protractor. And there you go. We have just done vector addition. Congratulations.